everybody. Welcome back to Markov. I'm really sorry about today, and especially to anyone who's walking into the room right now and finding nothing. But I'm glad you found us here. And yeah, how's the homework going? There's one I wanted to highlight in particular, and that was problem 3A. I just wanted to, you know what, let me just do that rather than say what I want to do, and then I'll ask you how the homework's going again. But there are three things I wanted to say about problem 3 and homework 5. One was I wanted to give you the bug matrix again because I don't have those solutions up yet. So the three things I wanted to point out for problem 3 on the current homework, it is a green bug, red bug problem. And it does depend on you having the transition matrix that you did compute for homework 4. And I don't have those solutions up yet. They'll be going up this weekend, but I wanted to make sure to give you the matrix. So this is a 4-leaf system. There's one red bug and anywhere from 0 to 3 green bugs on the system. And we were tracking the number of green bugs at time n. And we already talked about how to do this, and I'm sure you already did it yourself, but just in case you needed to know the answer because you weren't trusting your answer, that's the matrix you're going to need. So that's one thing I wanted to say. Another thing was in this statement in part A, it says initially a red bug is on leaf 1 and there are 2 green bugs on leaves 2 and 4. So the leaves totally do not matter. You know, the location does not matter. So really it could have said initially there's 1 red bug and there are 2 green bugs. I mean, I put there on purpose. You know, I want you to recognize when something doesn't matter, but then I felt bad about it. And the final thing is the question in A was to compute the expected number of moves until the red bug first eats a green bug. And this is a first step analysis. But I just wanted to emphasize again that first step analysis problems are not all the same. It's just the concept that is the same. I did 3 in class. One was an average number of steps to first hit a value. The second was if you're going to go until you have some kind of exit criterion, what is the probability that you exited in one state versus another? And the third was if you're going to start somewhere and go to somewhere, what is the expected number of visits to another state in between? Those are the 3 major ones, but you may have to do a first step analysis and alter your thinking a little bit. And this is one of the examples. So I wanted to say that I think it would be natural for you to say, okay, I want to know, I'm starting with 2 green bugs. So x0 is 2. And you might think that you want to know the first time that you are down to 1 green bug, but that's not going to do it because with 2 green bugs, the first move could be that the red bug jumps to the 1 empty leaf and then a green bug joins. So now you're up to 3 and then the red bug eats. So eating doesn't mean you went down to 1 because it could have meant you went up from 2 to 3 and then back down to 2. So I would just that's hard to write with notation. I would let T be the first time a red eats a green. And then you can still apply the same sort of first step analysis principles. So we would want, in this case, the expected value of T given x0 is 2. It's just that T is defined differently than it's ever been defined before. And we also would probably want to introduce the same sort of notation like a UI as the expected value of T given x0 is I. And then we'd want U2, but the final first step analysis is not going to look like any of the others. It's going to look like this. So I'll just do one for you. U2, the thing you want to find is the expected amount of time until the green bug is eaten. And so you have to take 1 step or no one's moving, no one's eating. And currently there are 2 green bugs there, 1 red bug and 1 empty leaf. So the red bug could jump to the empty leaf with probability 1/3 or jump to a green bug with probability 2/3. So with probability 2/3, the red bug jumps to green and it's over because there's 3 leaves he can jump to. And so there's no more steps. But then with probability 1/3, this is saying the red bug jumps to the empty leaf. And now what happens next depends on whether or not a green bug joins the grid. So with probability 1/2, okay, so after the red bug goes to the empty leaf, the green bugs are still at 2. With probability 1/2, no new green bug joins. So you're still at 2. And then with probability 1/2, a new green bug joins. So now you're at 3. So it's the same concept, but it's really different as well. So I hope that helps. Okay, we were talking about the exponential distribution and the lack of memory property. I was in the middle of that proof, which is quite short, and I want to prove the other direction, which is, I think, really interesting. The other direction being that the only continuous random variable that has the lack of memory property is the exponential. So the exponential distribution to us, I introduced some notation. Exponential. I'm going to write x squiggly line has the distribution exponential with rate lambda. And this is, I'm not going to talk about both of them this time. Last time I said there were 2 ways to write this. Now I'm going to talk about the one we want. This means the PDF is f of x equals lambda e to the minus lambda x for x greater than or equal to 0 and 0 otherwise. Not really important what happens at 0. If you wanted to flip where the equality was, that's okay, because we're computing area by integrating and finding it. We're computing probability by finding area under a curve, and there's no area right there on the line where x is 1. And we did see in this case, the mean or expected value is 1 over lambda, and we talked about how some people, a lot of people, will parameterize that, you know what, everyone, depending on the case, the scenario, what they're working with, is going to use one parameterization or is going to use them both at some point. Markov chain theory lends itself to thinking about rates. I already hinted that these are going to be inter-arrival times for a discrete state space. So we'll have some discrete state space that doesn't necessarily mean integers or positive, but it usually will. And the example I gave last time was this is, and going on up, that this is the number of customers coming into, the bank. And if you start with 0 customers in the morning, the first customer comes in after some random amount of time that we're going to end up calling T1. That's going to be an exponential distribution, at which point we jump up by 1. And then we go again until, well, there's more I have to say, how do customers leave? But the point is that we're going to have still a discrete state space. So ups and downs, but on integers, they don't even have to be +1 or -1, but the times between events are going to take on this exponential distribution. So we're moving from discrete to discrete continuous, depending on what order you say those words. Okay, so lack of memory is really important for us to keep the Markov property, because where you go should depend on where you are and not where you were. And so here was the lack of memory property or memoryless property. And lack of memory for the exponential distribution. Okay, so we have exponential with rate lambda, and the lack of memory property says that for any little x and little y greater than 0, the probability that x is greater than x plus y, given that x is greater than y, is just the probability that x is greater than x. So this is often examples of this, corny examples that are not really realistic, is a lifetime of a widget or a light bulb. And so if X is the amount of time that your electronic component will last, if you're given that it has lasted more than 3 years, the probability it will last more than 5 + 3 or 8 years is just the probability it will last more than 5 years. It's like just the random variable does not remember that we already waited those first 3 years. Okay, so the proof, before I prove this, I recap the PDF for you. The CDF is the cumulative distribution function for X. We always call that in probability and statistics, we denote it with a capital F. This is the probability X is less than or equal to X. And that's going to be the integral from -infinity up to X of the PDF. And in our case, the PDF is 0 when you get down to negative value. So it's going to be 0 to X and then lambda e to the minus lambda u du. If you use x's in there, no one's going to get hurt, but I find it a little weird to integrate with respect to x and then plug an x in. It's not weird. I don't know. Thing. But this is going to be 1 minus e to the minus lambda x. So that is the CDF that we're going to need. And the probability that x is, say, greater than x is 1 minus the CDF. So back to the proof, the left-hand side, I'm going to write that down. Y, and then x is greater than y. This is the intersection event over the probability of the second event on top, because everything is, the little x and little y are positive. Then we've got redundant information. It's kind of like saying, what is the probability that x is greater than 5 and x is greater than 3? That's just the probability that x is greater than 5. So for that reason, I get to rewrite this numerator with just x greater than little x plus little y. And so these are 1 minus the CDF. Here is the CDF. 1 minus the CDF is just this part. And we're going to plug in x plus y and y. So I get e to the negative lambda. Maybe I'll write one more line. This is 1 minus the CDF at x plus y over 1 minus the CDF at y. And that is 1 minus a 1 minus. So you get e to the negative lambda x plus y over e to the negative lambda y. And that thing on top can be factored. And the y part will cancel. So we've got e to the negative lambda x, which is 1 minus the CDF evaluated at x, which is the probability that x is greater than x. And that's what we wanted to show. We wanted to start with the thing at the very top left of the screen and show that it's the thing at the bottom right. The one thing I always found really cool about this is that the exponential random variable is the only continuous random variable with this property. And that seems harder to show, but we're going to show it, because what do you have to work with if you don't have the distribution? Just because we're here, on the flip side, I want to say for the discrete case, the lack of memory property happens if and only if your random variable has a geometric distribution. So the geometric is a lack of memory or memoryless variable in the discrete setting. So let me write the statement here with a nice little star kind of thing. The exponential distribution is the only continuous distribution with this property outside of maybe like a shifted exponential. Let me finish writing this though. Distribution with this property. So what I was trying to say at the same time was maybe you have a random variable that takes on only negative values or both negative and positive. If it's negative valued or negative and positive, then no, it can't be an exponential distribution, but it's going to be maybe a shifted exponential distribution or a flipped over the y-axis. So it will still be exponential type in those cases. But we are going to prove this using, assuming we have a positive x. So I want to suppose that x is a non-negative or positive. In the continuous case, it won't matter. continuous random variable, that's random variable, such that this lack of memory property holds for all little x and little y greater than 0. This is not required. Again, we might be moving the exponential around on the axis or flipping it, but it'll just make for a cleaner proof if we assume that right now, that everything is non-negative. So if you write this out as the ratio it is, and then cancel that one redundant thing out in the numerator, and then multiply the denominator to the other side, this implies that the probability that x is greater than x plus y is equal to the probability that x is greater than x times the probability that x is greater than y. So that is me just rewriting this and moving things around and also taking out that redundant piece of information. And these are all so-called tail probabilities. And it's going to be convenient for us to have a notation for this function of x that is not 1 minus the CDF. So a common notation for tail probabilities is to make it look like a CDF with a capital F, but put a line over it. This is defined, so I'll put a colon there, that means defined. This is defined to be 1 minus the CDF, which is the tail probability that x is greater than x. And using that notation, over here on the left, we've got capital F bar x plus y equals capital F bar of x, capital F bar of y. I'm going to subtract an F bar of x from both sides. And so that's going to be, it's going to end up subtracted over here. And I'm going to go ahead and then factor out that F bar on the right side. F bar x. How about big? Times 1 minus F, the other way around, sorry, F bar y minus 1. Again, I just subtracted F bar x from both sides and then rewrote the right-hand side. Some of you know where I'm going, maybe, and that is I'm trying to see like a derivative and make a little differential equation. I may move this again, it's always in the way, really small, right there. If I divide this left side by y and then let y go to 0, then the limit is the capital F bar derivative of x at x. And I want to do something similar on the right side, and I can get away with it there because check this out. I can rewrite this 1 as F bar of 0 because that is the probability that x is greater than 0. And that is 1 for this continuous random variable, which can't actually equal 0 and certainly won't be negative. So I can replace this 1 with this F bar 0. And I'm going to do that, and then I'm going to divide both sides by y. Okay, so on the left, I've got F bar x plus y minus F bar x over y. And on the right, I've got what I've got, F bar x. I'm going to move down, give myself more space down here. And that is times F bar y minus 1, but I'm rewriting the 1 as F bar 0. And I put a y in the denominator on both sides. So now let y go to 0 on both sides. I'm not going to rewrite the line just to put limits in front, but if you have the limit here as y goes to 0, then on the left, you've got F bar prime of x, you've got a derivative. On the right, if you put a limit here, you can pull this out of the limit because that's not changing in y. So that F bar x is just going to be sitting out front, And then the limit of this as y goes to 0 is the derivative evaluated at 0. And this is a constant, and that's all I want to think of it as, constant. And I could actually tell you whether it's positive or negative right now. I want to call it like C for constant, but C is going to turn out to be a negative number. And I think it's a little more clear if I call it negative C, where C is positive. I know this is negative because F bar of X is the probability that X is greater than X. And so as little x gets large, it's harder and harder for big X to be above it. So the probability is getting smaller and smaller. This is a decreasing function of X. And so the derivative is going to be negative. And so that's why I know up here that this is a negative constant. So I could call it, say, C, where C is negative, but this is going to look cooler if I call it negative C, where C is positive. So we have F bar prime of X equals F, let me put the C in front, negative C F bar X, where C is some constant greater than 0. Now everyone's in on the joke. I'm trying to find this PDF and say, hey, this must be an exponential distribution. So I don't know how up everyone is on their differential equations, but you would you would divide and put both of the F bars on the left side, and then integrate both sides with respect to X. And so like a dx equals integral dx. So on the left, we've got the derivative of the log of F bar. This is actually the derivative of the log of F bar X. So if you're integrating the derivative, you're just going to get that log back. So on the left side here, I have the log of F bar X plus a constant, but I'm going to wrap the constants into 1. On the right-hand side, if you integrate this with respect to X, and it's indefinite, you get negative C of X plus another constant. So this is both of the constants wrapped together, rather than plus a constant on both sides. And finally, F bar X is going to be e to the negative cx plus d. Now, if you factor that into e to the negative cx times e to the d, then you have another constant that I'm going to call like a. So in case you lost it, a is actually e to the d, but I don't really care. And finally, to find the constant, I want to use the fact that F bar of 0 is going to be 1. And if I plug in 0 to this thing, I just get a. So a is 1. And finally, put it all together, F bar X is e to the minus Cx. So Fx is 1 minus this F bar is 1 minus e to the minus Cx. And this is the CDF for an exponential distribution with rate C. And if you don't like identifying distributions with CDFs, I think it's more natural to think PDF, because that's how we define the distribution. The exponential distribution has this PDF, and the normal distribution has this PDF. Then take the derivative of this, and you'll get C e to the negative Cx. And that one you should definitely recognize as an exponential PDF. But this is the CDF of the exponential with rate C, which finishes the claim that if we start with the lack of memory property for continuous random variable, that we necessarily have an exponential distribution, unless the random variable can take on negative values, but then it's still going to be kind of exponential, shifted or flipped or something. Okay, so exponential distribution is going to be super important for study of continuous time Markov processes. We haven't really given the Markov definition in continuous time, but I bet you could kind of Yes, I mean, the informal definition is going to be at any time, which is no longer going to be at like a time point, 1, 2, 3. But if you just go in and look at the process at time 23.7, where you go next depends only on where you are, not where you were, not how long you were where you are. And so we really need that lack of memory property to talk about continuous Markov chains. And we'll prove that eventually, given the actual definition that the inter event times for a discrete state, continuous time Markov chain, going to have to be exponential. So clearly an important distribution for us. And the last, okay, so I was in a list of some continuous random variables. I don't know what I titled it, but last time I started, don't write this again, but in case you're trying to see where the notes went, like I wrote some kind of heading like continuous random variables. And then one, we talked about the uniform on A to B, but really we mostly only need the uniform 0 to 1. And then 2, we talked about the exponential distribution with rate lambda. We also talked about how it could be parameterized differently. And so that's why I'm now writing a 3, is the third and final distribution that we really need to get going here is the gamma distribution. The continuous random variable x has the gamma distribution if the PDF looks like this. So f of x is 1 over, so it's going to have 2 parameters. I like to call them alpha and beta. Some people call them lambda and beta, some people call them a and b, and a lot of people call them alpha and beta. So there's 2 parameters here, an alpha and a beta. They both need to be greater than 0. Like if the lambda wasn't greater than 0 for our exponential PDF, it wouldn't integrate to 1, it would blow up. So there are some restrictions on the parameters. But the PDF is 1 over something known as the gamma function, which I am going to define if you haven't seen it. The gamma function of alpha, beta to the alpha, x to the alpha minus 1, e to the minus beta x, for x greater than or equal to 0 and 0 otherwise. Where again, this is something known as a gamma function, which I'm going to define in a minute. And it is related in many ways to the exponential distribution. One thing I can kind of easily see is in the case where alpha is 1, I'm going to get x to the 0, so that's going to disappear. And I'm going to get beta to the 1. So essentially, when alpha is 1, I'm going to get 1 over gamma of 1, beta e to the minus beta x. And this is going to hold for x greater than or equal to 0. So that's going to force, although we'll show it, that's going to force this must be 1. It's going to force it to be 1 because I know that this integrates to 1 because it's an exponential PDF over that range. And so if I put a number like 3 in front of it, it would integrate to 3. So the point is that for alpha equals 1, we have an exponential distribution as a special case. Just like the exponential distribution, people will parameterize this in 2 ways. So instead of the beta that I have, they might have a 1 over beta everywhere. I'm parameterizing in the way that will sort of correspond better to how we wrote the exponential. So just be careful. We're going to write x squiggly line has the distribution, a capital gamma, and then alpha and beta. I don't really think it's worth messing this up by putting like, this is a rate or an inverse rate or whatever this is. If you see this written in a textbook or a journal article, it's really, in my estimation, about 50-50, whether you're going to have this PDF or the 1 over betas. So just be careful if you're looking stuff up on the internet or in a book that you're working with the right gamma distribution. And if you're not, you just need to put 1 over. It's not a big deal, but the alpha is known as a shape parameter. because it really controls the shape of the distribution. By the way, still haven't defined this, but it's just a constant. Not only is the gamma part just a constant, but this is a constant as well. So the kinds of shapes we can get out of this, alpha did need to be greater than 0. And if it is greater than 1, then you have x to a positive power. And when you evaluate that at 0, it is actually equal to 0. And the x to the positive power is going to be something increasing, but eventually the e is going to drag it down. If you get a picture, not really that a drawing, but kind of a skewed bump like this. And if alpha is equal to 1, then you're just left with this, which is not normalized. I don't have the right constants, but you can see that if you're just left with this, when you plug in x equals 0, you're at 1, and then you're going down exponentially. So I guess I shouldn't put the 1 here because it's actually going to be the beta constant that we need to make that a proper PDF, but it's an exponential distribution. And then finally, if alpha is between 0 and 1, then you have x to a negative power. And if you plug in 0, you have like 1 over 0. So it is blowing up at the y-axis. You get something that is just asymptotically approaching the y-axis and then coming down. Okay, I need to define the gamma function for you. This is something we're going to use a lot. There's a couple of capital gammas already in these slides for today. If you see a capital gamma in probability or statistics with 2 arguments, no matter what they are, if they're alpha, beta, or something else, this is referring to a distribution. But if you see a gamma with 1 argument, even if it's not called alpha, this is referring to the gamma function. And the gamma function is defined for alpha greater than 0. Gamma of alpha is defined, and that's what that colon means, not just equal to, but it's defined this way, to be the integral from 0 to infinity of x alpha minus 1, x to the alpha minus 1, e to the minus x dx. So check this out. If you look at the PDF for the gamma and you integrate like 0 to infinity, beta to the alpha, ignoring the gamma part, x to the alpha minus 1, e to the minus x dx, minus beta x dx, you can put alpha minus 1 of these betas together with the x. So you have beta x to the alpha minus 1, e to the minus beta x, and then another beta dx. And if you let u be beta times x, then you're going to get the integral of u alpha minus 1 e to the minus u du. And because beta is a positive parameter, when you plug in x equals 0, u is still 0. And as x goes to infinity, u goes to infinity. And so this is the integral defining the gamma function. And what I started with is most of the PDF, and it integrates to this. So if you put 1 over this in front, you have something that integrates to 1. It's kind of a lazy distribution in that sense. Make up your favorite non-negative function that is integrable in the sense that it doesn't blow up. Integrate it over whatever range you care about. Call that a constant, name it after yourself, and put 1 over that in front of your function, and you've got a PDF. This is just the right constant. And it has a lot of great properties. We're only going to need 3 properties. And so I want to get back to Markov chains. So I'm going to talk about only these 3 properties. And I think maybe I'll speed up a little bit. So the first, let me remind you over here, since it's off the screen, is the gamma function. So the first is that, and we do need alpha greater than 0. The first is that gamma of 1 is 1. This is super easy to see by plugging in 1 for alpha. This part disappears. And now you can either do that simple integral, or you don't have to do it at all, because what's left is the PDF of an exponential with rate 1. And over 0 to infinity, we know that PDF has to integrate to 1. So this is proven by just plugging in alpha equals 1 and doing the integral, which you probably don't have to do if you recognize it as being the integral of another kind of PDF. The second thing is for alpha greater than 1. If you look at gamma of alpha, I am going to streamline this just a little bit. If you try integration by parts on this, so integrate by parts, that's the integral of u dv is u v minus the integral of v du. And if these are definite integrals, then in this uv part, you would have to evaluate it. So if you let this be, did I lose my, no, I didn't. If you let this be u and this be dv and integrate by parts, it's really not hard, but I don't want to spend time on the integration right now. You will get down to alpha minus 1, gamma of alpha minus 1. And the alpha minus 1 comes from the fact that when you are taking the derivative, the du, you get an alpha minus 1. That's the derivative of this with respect to x. And then x to the alpha minus 2, which is setting the stage for the gamma function evaluated at alpha minus 1. It's not hard to show, it's just kind of busy work. And I want to get back to the Markov chains. Okay, the third property, this one you're going to get the most use of in this class, is for an integer n greater than 1. So this means, greater than or equal to 2. Gamma of n is n minus 1 factorial. And you can show this by just using the last property. Gamma of n, we know by the last property, is n minus 1, gamma n minus 1. And if you use that again on gamma n minus 1, you lose 1, you go down by 1, so you get n minus 2, gamma of n minus 2. And if you keep going to the bottom, you will eventually get to n minus 1, n minus 2, down to 1, gamma of 1, but gamma of 1 is 1. So you can see the n minus 1 factorial. The factorial doesn't make sense for a non-integer because you're subtracting 1, you might just skip over 0. There's going to be no bottom. So we have the distributions that we're going to need. And I have one fact I want to tell you before we talk a little bit about simulation of continuous random variables. So fact. This fact is that if you take independent exponentials with the same parameters, so we say independent and identically distributed, and you add them up, that new random variable that is the sum of the individual random variables, that is going to be have a gamma distribution. So if x1, x2, xn, and I'll try to not use too much excess notation, are independent and each is exponential with rate lambda. So independent and identically distributed, the fast way to write that is x1 out through xn, squiggly line with an IID, and then give the distribution. Then a new random variable y, computed as the sum of the xi, will have a gamma distribution, which has two parameters. The first parameter is always the number of things you summed. And the second parameter is going to match that of the exponential distribution, assuming you are defining the exponential distribution with a rate and the gamma distribution the way we have, with our betas in the place that they are. So we already talked about how a one particular gamma with the right alpha is exponential, but now we see that we can get a gamma out of summing exponentials. And usually this is proven using moment generating functions, which is something that's done in mathematical statistics. I don't know all the different codes with the stat now, but it's APPM 4520, 5520, and other things. If someone was going to prove it in a Markov process course, they would probably use something known as a probability generating function, because Markov chains, it's a different kind of thing, like a moment generating function, and depends on which angle you come at this stuff from. If your background is in stochastic processes or statistics, some people think rate, some people think mean, some people think moment generating functions, some people think probability generating functions. And I don't even want to take the time to tell you what those are. So what I'm going to do is on your next homework, and we need to talk soon with an exam coming up, but I'm going to let you convince yourself of this fact by simulating some exponentials, adding them up, doing that repeatedly, making a histogram, and then overlaying the histogram with the gamma PDF to see that it matches. So we'll convince ourselves of this fact using simulation, which, by the way, is something I do all the time, in research math, when you're trying to prove something that no one knows before and you've written down some cases. I use simulation all the time to help me. If you've ever done research, right, you can bang your head against the wall for a long time and sometimes even begin to doubt your conjecture. So I use MCMC, Markov chain Monte Carlo simulation, all the time to prove results, not to prove, to bolster my opinion, to say I'm starting to worry that this is not true, but let me simulate it and see what it says. So I use simulation to do pure math and proofs when I'm feeling doubtful, because it helps me press on with the proof. Okay, how can we simulate the exponentials? So we are at a simulation break. Suppose that x is continuous. So this is going to be our first example of simulating from a continuous distribution, because so far we've talked about discrete and we had little boxes and tabular things and we chopped up a number line. So suppose x is continuous with CDF, so cumulative distribution function f of x. Furthermore, suppose that this is invertible, which is not always the case. You take a random variable u from your random number generator. So this is going to be something with a uniform 0-1 distribution that's going to be spit out by a random number generator. Then the new random variable that you can form by plugging that into the inverse CDF. So this is a CDF with a random variable plugged in, which this whole thing is random itself. This has the same distribution, we're going to prove it, as x. If this has the same distribution as x, and we want to generate x's, what we can do is just generate uniforms with our random number generator and plug it into the inverse CDF. And the result is going to be a list of numbers representing x's that should match the PDF for the x distribution if you make the histogram in the right way. Now, CDFs are not always invertible. They are non-decreasing, but they can flatten out and not be strictly increasing. And there's even very, very common cases where we can't write down the CDF, the normal distribution, like everyone's basic continuous distribution. The CDF has no closed form expression. So in that case, you wouldn't be able to simulate in this way. And that's what keeps me in business. If you can't simulate this way, then you move on to your next tactic, which for us is going to be the accept reject algorithm. And that's going to require that you be able to bound something. And if you can't do that, you move on to your next tactic. And if you can't do that, your next one. And that's what, again, keeps me in business, because there is no one recipe to simulate all random variables, much less all continuous random variables. Okay, I'm going to prove this is going to be really rushed. You know what? I'm going to end there, but if anyone wants to stay on, then I'll prove it now because I hate ending in the middle of something like that. So thank you all for being here in our virtual space and allowing me to get to my talk at 3. So I'm going to end the lecture, and if anyone wants to stick around, I'm going to do this proof, but I will start with it next time on Markov processes.